Hi. Thanks a lot for the organization, for the invitation. It's really, pinpointing exactly the topic, one of my favorite topics, maybe the most favorite topic, which is not just stable phases in noisy quantum systems, but the question of how does the transition from quantum to classical occur in noisy quantum systems. So I have a confession. When I did my master's at Weizmann Institute, I kept hearing this notion of how to move from quantum to classical physics by taking h bar to 0, and I never understood it. I don't know if anybody does, but to me it didn't make sense, and I always wanted to have a different explanation of the transition and how it occurs. So I think that we made some progress, some interesting progress, on a line of works that has been going on since the fault tolerance theorem, basically, and even before that. So I want to tell you the story. It's very, very much work in progress, but I hope it will be somewhat interesting. Okay, so this is, very importantly, it's joint work with my student Noah Fixler, who actually should have given a talk today, but she's just given birth to a beautiful, very cute little daughter, so she's not here. She will be here in a month. So you're welcome to ask her many questions when she arrives with the daughter. Okay, so let's look at what we knew maybe, what was it, almost 30 years ago. Okay, I'm going to try to reach this point. And this is the line. It's supposed to be a straight line of the noise rates, eta, that goes from 0 to 1 in a quantum system, many-body quantum system. And what we knew a long time ago was that there is a point here, maybe back then was 10 to the minus 6 or maybe 10 to the minus 3 or something, which is the threshold, the quantum threshold. And here we know that this is BQP, quantum universal. And we knew also, that was actually my first paper that came before the fault tolerance paper that led us to the fault tolerance paper. We knew that for eta very large, larger than 0.97, there are classical simulations, efficient classical simulations. And the reason I'm saying that this led us to the quantum fault tolerance result is that basically there was something that didn't work below a certain error rate. Yes?
So just make sure, are these errors in like the dynamics of the circuit, or we're just trying to preserve a state?
They're in the dynamics of a circuit. So I'm talking, I'll define in a moment what the model is, but I'm talking about a noisy quantum circuit with some error probability per qubit or per gate or per qubit per time step. Okay? And this is eta. So it goes from 0 to 1. So very simplistic model for now and also throughout the talk, maybe. Okay, so so this is Aharonov-Benor 96. And this is Aharonov-Benor 96 and Neil Laflamme and Zorik and Kitaev. And okay, so we know that something is going on in terms of computational aspects of the transition from quantum to classical. Here we have universal quantum, meaning the ability to manipulate, to control quantum states and quantum evolution in order to extract universal quantum computation. And here, this is not the case. We have classical efficient simulations. So in some computational sense, we describe this as macroscopically classical. There's no real way to describe it in a physics sense, but computationally, we have something that really distinguishes between the two. And so what's going on in between? And how to describe it also physically, and how to describe it from entanglement point of view. And And is it really a transition as a phase transition? Is it really something that occurs at a particular point below which there is macroscopic quantum behavior that we can control and above which there is globally classical, or is it something else? Okay? Okay, so in an attempt to approach this problem already, so let's start really a long time ago, 99. I tried to come up with some explanation for this in a paper which is called A Quantum to Classical Phase Transition in Noisy Quantum Computers. Okay, and here the model is you have a circuit, and let's consider a 1D or a constant dimensional circuit with alternating gates like that, so nearest neighbor gates. And I also allow reset gates. This is time 0. Sorry, this doesn't actually exist. And this is time. And these are the qubits. And I also allow reset gates. Okay, so these are the gates. There are noise operators that act on the system independently on each qubit in between the time steps. And I also allow a reset gate before the gates apply. Okay, at any at integer minus epsilon time. Okay, good. So this is the model, and what I defined in that paper was entanglement length. And entanglement length would be the following thing. So if I have two sets of qubits, A and B, and the distance between them is D, I'm going to say that the entanglement length is psi if the entanglement behaves like this. If it's bounded, exponentially bounded in the distance, with a entanglement length psi. Okay, so what is shown in this paper is that there is a phase transition in this entanglement length for eta less than eta threshold. Let's call it this. Psi is infinite. And for eta above this eta, for some eta, I'll say what it is in a moment, this is finite. Yeah. This is for any initial state, in fact. But it goes. But this, I'm actually glossing many details without describing them. But this is basically averaging over time. Okay. So take polynomial in the size of the system, average over this. This will be the behavior for any initial state, because there will be, if you're above some threshold, and if you're below the fault tolerance threshold, you can actually achieve this for some state. So there exists a state. Or there exists, and a different way to say it is there exists a circuit. So I can choose these interactions in a non-homogeneous in time and space. Okay? Yeah.
What's EAB?
EAB is the entanglement information between A and B. Thanks.
In what sense? What's your measure?
Entanglement of formation. Okay? Average over, so minimizing over the best way to represent the density matrix and taking the entropy of entanglement. Yeah. So, okay, great. So, this is for any constant B. Okay, and basically this relies on the fact that, first of all, on this side, there is infinite entanglement length, and the reason is that we showed in the original fault tolerance paper that in 1D and in any constant dimension, you can actually implement fault tolerance quantum computation. And therefore, you can generate a highly entangled state, separate the two parts, and maintain it for a long time. And therefore, there is no decay of entanglement in the distance, and therefore, that's infinite. Okay? So we can show that for some circuits, for the fault-tolerant circuit. And you can show that for any circuit, and this paper, this is what it shows, that for any circuit above some point, the entanglement length is finite. So let me sketch the proof, unless there are more questions now. Okay, so I want to sketch the proof of this, because it will come in handy. So basically, the idea is the idea is to look at the density matrix evolving in time and to write it as a mixture of states. Rho will be sum over all the noise events. So best to keep in mind that at each point here in between gates, the qubit is, for example, measured in the computational basis with some independent probability eta, or replaced by a completely mixed state with some probability eta. Okay, some entanglement breaking event. Okay, so I'm averaging over the noise events times the probability of the noise event. The probability of the noise event times this density matrix, rho of the noise event. And the point is that with high probability, all but something very small, these are going to be tensor products of small clusters of qubits. Okay? And the way small sets of qubits. Okay, so moreover, the probability for A in A and B in B, where A and B are distant D apart, to be in the same cluster here is going to be decaying exponentially with the distance. Okay? Okay, so how does this proof work? Well, let's just see, let me describe how the clusters work and then how to show some bound on the sizes of the clusters. So the clusters basically are going to work to have the following dynamics. So you start from a state which is completely separable, so a tensor product. So the clusters are all single qubit clusters. And then every step you update it by, so you basically simulate exactly what the circuit does. So if there is an entanglement breaking event, say depolarization, then that qubit is replaced by a completely mixed state. And then we do that for all. We replace the reset gates for all. And then there is a unitary that is applied, which means that clusters unite. Okay? And then again, you repeat. And note that, for example, if here the cluster, those qubits are in one cluster, and those qubits are in another cluster, and this qubit is in another cluster, then if this qubit is being depolarized, then those qubits remain in the same cluster. And that qubit separates to another cluster. Okay? And now I need to bound somehow the size of the clusters. Yeah?
What defines the cluster?
So I've just defined it. It's a definition by iteration. And it basically is defined by the circuit and by the noise process. So it's a noise event defines the clusters.
What do you do with the geometry of the circuit? Like, what do you do to
It's not just the geometry, because it depends. So if I didn't have noise events, then the cluster would basically immediately become the whole set of qubits. But the point is that there is sort of a competition between the unitaries that unite clusters and the noise which separates qubits from the clusters. Okay, so for each noise event, meaning for each choice of which qubit depolarized at each point, you have a different evolution of the clusters. And this corresponds to a mixture of density matrices, each corresponding to, where are you? Each corresponding to those cluster partitions. Okay? Yeah.
If I know that I have two things that are in the same cluster, how much does that tell me about their entanglement
That's a great question. Can you keep it for later? Okay. Okay. Good. So how do I analyze the sizes of the clusters? Well, it is possible to actually map this process to a percolation process. So I can actually look at this circuit, and whenever there is a noise process, remember, say each qubit is measured with probability eta, I will cross, if that happens, I will cross the edge connecting the past of the qubit to the future of the qubit at that time, step. Okay? So I'll cut the timeline of this qubit. Okay, and for convenience, I will contract edges that go along those unitary gates because nothing happens to them, so they always unite qubits. Remember your question. And that means that I have a tilted 45-degree percolation, 2D grid with percolation on it with probability eta. Okay? Sorry, I mean, this goes that way. You see the picture? So basically, because those points were united to 1, I have something like this. And this edge is really is erased with probability eta if this edge is erased with probability eta. Yeah?
Just make sure your error model is you apply depolarization and then you immediately reset. Is that right?
I don't immediately reset. No. Reset gates, no, sorry. Let me redefine the model. I have a circuit, and somebody told me, you can tell me which circuit you want to implement, and you tell me where the reset gates are. That's the noiseless circuit. If you can insert them wherever you want, you can insert unitary gates here, whichever ones you want, etc. You have a circuit. And then on top of that, I run a noise process, which depolarizes qubits with IID probability eta. And that's the model for fault tolerance in our paper, actually. Of course, with a specific construction of the unitaries, etc. And also, okay. Okay. Reset gates are absolutely essential in order for fault tolerance to hold, right? Because if you don't have reset gates, then entropy accumulates, and basically after logarithmically many time steps, yeah, or whatever. However, I mean, nobody says specifically in fault tolerance and everywhere, error correction, that's what we do, but we don't have to do that. Yeah.
My confusion is once you completely depolarize, that qubit can no longer participate and entangle with other qubit unless it's being reset. Correct? Say you try to replace this qubit by a maximum mixed state, then no longer whatever unitary you apply.
Well, you can think of other qubits mixing it, swapping it with some probability, etc. You can think of many things. So that particular qubit is going to, that particular location could be made, could be reset by other qubits, etc. You're right that if I just use it as is, then it's completely mixed. Okay, so I've mapped it to a percolation process, and now the point is that there is in that paper there is a correspondence lemma. Which basically says that, well, if a qubit is here at time t, is connected in the past, suppose these were the noise events, the faults basically, and suppose here you can see that B is connected to A. Let me do it in red. It's connected, even though there was noise, it's connected to A. Then A and B are going to be in the same cluster at time t. Okay? So this is the correspondence lemma. And with that, basically, you can show that if you now analyze the percolation, basically it shows that there is a correspondence to percolation. Percolation on the space-time of the quantum circuit. And as we know from percolation, above the critical point, where in percolation it's the opposite, but let me use here our convention. When eta is larger than the critical point, then there is a decay, exponential decay in the probability to percolate over distances. And below that, there is a probability, a constant probability for a giant component, for basically an infinite component. And if you cut it to a finite size, then there will be some probability, constant probability, for a linear size connected component. Yeah?
The eta threshold C, which you prove, may not be the threshold, but that is a value where you prove you have a percolating phase. Is that true? So that might not be the threshold, true threshold?
Right. So this means that the percolation threshold, at the percolation threshold, there is finite correlation, finite entanglement length. So above the percolation threshold, eta above the percolation threshold, there is finite entanglement length because what this percolation model basically shows is that for A and B, which are distant apart, which are far apart, with high probability, with that up to this probability, there will be in tensor product. Okay, so you can approximate the density matrix by basically a density matrix in which A and B are in tensor product, plus something which is exponentially small in the distance. Which means that there is a...
Do you think the transition is a usual percolation transition?
No. Wait, I'm just saying a fact from 99. Okay? I'm trying to get to 25. Okay, so that's the correspondence lemma. Okay, so good. So we have this finite entanglement length. We also have efficient classical simulation. So with this at that place, right? When eta is large above the critical point, the clusters are going to be small, which means that we can update them, which means that we have an efficient classical simulation of the system. So here we have now it's here, 0.5. That's the percolation threshold for dimension 1. And we have here simulation, efficient simulation. And we have here finite entanglement length. Okay? That's what we know. Okay, good. I should mention that this also works for higher dimensions. For higher dimensions, the critical point, the eta percolation, critical is less than 2/3, larger than 1 minus 1 over 2 to the 1 over dimension. Dimension here is the dimension of the circuit, not the actual dimension is d plus 1. And note that for higher dimensions, just as a small remark, if you write the quantum circuits like that, with alternating, so you have a quantum circuit in higher dimensions where, say, you rotate between the directions in which you actually apply the gates. So so basically, if you contract around the points here of the gate, you will get a degree 4 graph. So it's not exactly a d plus 1 dimensional lattice, just a small point, but it behaves essentially the same. Okay? Good. So we have this picture, but this is a very, very still not satisfying picture because we don't know what's going on in between. I should just say that there has been a lot of work since then about quantum simulations. I cannot really put the points, not just because it's too high for me. It's simply I don't know where to put them because there are different models in which this is done. And this is, as I said, work in progress. We haven't really done the work to actually compare between the different points, but there's been a lot of work on quantum simulations, classical simulations of highly noisy systems. For example, works by Vermani and Planio showing near Clifford, where enough noise actually makes things Clifford, and enough noise makes the operations entanglement breaking, etc. So simulations using the fact that locally the system becomes classical. Okay, good. So there are many points here. There are obviously also many points here with improvements of the fault tolerance constructions. But still, this picture is very full of open questions. Okay, so this is where this is where I asked Noah to join this search and investigation, and I think one maybe an important step, maybe the most important step, is to give the right definitions. And one definition which I want to place here is the following definition. Okay, so notice that in this picture, if we have a connection between qubits, and I'll be very sketchy here, a connection like that between two qubits, A and B at time t. And imagine that everything else is erased. That's the only thing that is left by the noise event. Will those qubits be entangled? If that's exactly the picture. Yes? No? No, they will not be entangled because so imagine this is very long, and the reason why they will not be entangled is that their light cones don't intersect. And this has been known, I mean, it's a trivial fact, appears also in our paper with Kitaev and Nissan about quantum circuits, but was discovered over and over and over again that if the light cones don't intersect, states are in tensor product, obviously, and so there's something that goes to Fiona's remark also, that somehow, even though these are connected, it doesn't tell us the full story about entanglement. Okay, so the connectivity in this early paper is not catching the full story. What is catching the full story? Well, I don't know, but let me put a better definition, which is light cone connectivity. I'm now asking, what's the probability for two qubits to be not connected, but light cone connected, meaning that their two light cones intersect. Okay? And this allows them to be entangled if they intersect. Okay, so basically we can now look at, so that's the first step. We can now look at, it's a critical for light cone connectivity. And like in every statistical mechanical model, you will have a critical point above which there is exponential decaying probability for light cone connectivity, and below which there are many, a constant fraction of qubits that are light cone connected. Good. So it turns out that what I want to say now, okay, so the one thing we want to show is, the one thing I want to mention before as a first thing is, where does this lie compared to the connectivity threshold? Is it to the left or to the right? Sorry?
The light cone connectivity depend on time?
Yes. It's given a noise event. It's given a noise event and depends on time. So the light cone connectivity not between qubits, but between qubits at a given time. And for a given noise event. Okay? So we are looking at a statistical physics model, and we're basically averaging over it. And so this light cone connectivity works for every one of the events separately. Okay, so let me rush through the, let me continue to the, the years are, need to go to somehow to reach 25. So the one thing I wanted to say is, first of all, eta light connectivity, the critical point, is going to be smaller than that, right? It's easier to be connected without light cones than with light cones. So that's going to be preserved for larger noise processes. So it's somewhere here. And it turns out, by a result by Grimmett and Heiner, who are probability theorists, that basically this property or this threshold is equal not to the percolation threshold, but to the threshold of directed percolation. So directed in time. Okay, that makes sense. Let's call it directed percolation. Okay, and that's known in 1D, and that's 0.37. That's directed percolation. And it can be easily shown using the same argument that I showed before, that above this directed percolation, psi is finite. By the same argument, right? So basically, you can look at this, at A and B, and A and B are going, if they're distant apart, if they're far apart, then they're not going to be light cone connected between any of them, and therefore the density matrix can be written, approximated by a matrix in which they're in tensor product. Okay, so above the light cone connectivity threshold, this is what's going to happen. So the entanglement range, entanglement length is finite above it. Just a moment. Yeah, okay. Yeah?
You're dealing with a fault-tolerant circuit. You're doing error correction. There is some LOCC operations, so there could be teleportation.
No LOCC operations. Everything is quantum. Everything is encoded here. Everything. There's no classical operation on top of that.
So, but to get fault tolerance, you don't need...
No. 97 paper shows that you don't need that. Everything can be done without measurements. The only thing that you do need is reset gates. You can do that in 1D. You pay a lot by the threshold, but there is a constant threshold. Okay, so good. So psi is finite, which means that okay, we moved here, and we know that the entanglement length is going to be finite, which means that there's no memory, no quantum memory above it. I won't describe this unless asked later. And it basically means that there's no quantum computation. But does it mean that there is quantum simulation, classical simulation, efficient? So, okay, so what do you think? So we know that the entanglement length is finite. It seems that there's no long-range correlations or no long-range entanglement. Should we be able to do classical simulations? Okay, so the argument about the clustering doesn't work. The reason why it doesn't work is that even if there is no... Okay, the reason basically is that if you have a cat state, then it's true that A and B are not entangled, but there's no way to cut it to a tensor product. So the fact that the entanglement length is finite doesn't mean that you can actually cut things to tensor products. So we need somehow to be able to define things such that you actually can cut the state to tensor products. And this is done by, what can I erase here? By a better definition, which is zigzag connectivity, which is a transitive version of the light cone connectivity. So I say that two qubits are zigzag connected if there is a way not to connect them this way, but to connect them this way, such that this is light cone connected to this is light cone connected to this, etc. There's a chain of light cone connectivities. Okay? And this zigzag connectivity is a transitive relation, and therefore you can actually divide the sets of qubits to clusters, and you can show that if you are above the zigzag connectivity threshold, eta above the eta zigzag connectivity threshold, then there are small clusters, and you can do classical simulation, efficient classical simulation. The way to do that is by basically keeping track of the light cone connectivities, pairs of qubits, whether they're light cone connected or not, and somehow iterate the simulation classically so that if you have the zigzag clusters, you can, once you have them, you can apply the unitaries. They unite to large clusters, which may not be the small zigzag clusters. They may be larger, but you can actually find out, because you know the noise process, you're simulating it, you can find out what are the zigzag clusters, and you can take the clusters and reduce them to the zigzag clusters, and therefore you have a classical simulation, efficient simulation. So now you have ZZ here, which is somewhere here. It's above the light cone connectivity threshold. I'm sorry?
So there should be a requirement of how many zigzags there should be?
Infinitely many, as far as unboundedly many. You want a transitive relation. So okay, so now, above the zigzag connectivity threshold, there is classical simulation. Okay, so now the question is, where would this fall? Is it close to the light cone connectivity threshold? Is this sort of, so remember my question, is there a single point that's interesting, or many, or more than one? Just a moment. So the question is, do you think that it's here, or do you think that it's closer to the percolation? Think about your question for a moment while I'm telling you why it's very interesting, this question. The reason it's interesting is because if the two are different, if there is light cone connectivity threshold and the zigzag connectivity threshold is different than it, then there is an intermediate phase in which you have an area where light cone connectivity is no longer there, so entanglement length is finite, and yet you cannot perform classical simulations, which means that something very interesting is going on there. There is no quantum memory, but there are quantum correlations that are long range. And this is really an interesting phase.
Below zigzag connectivity, can you guarantee that there does not exist classical simulation?
No.
So
Thank you. This is, I'll get to that. It's true. This is an indication that something like that exists. It seems to be suggesting that, but you're right, it's not true. Yeah?
Can we be more precise what we mean by classical simulation?
Efficient classical simulation, meaning a classical algorithm that works in quasi-polynomial time, and basically outputs exactly the measurements that you would get from running the quantum circuit with that noise process.
So it will allow some epsilon error.
You don't need any epsilon error. I allow it, but you don't need it.
I just want to make sure, so suppose I'm working in 1D, and the zigzag connectivity, does that mean that it has to be light cone connected to all of the, so A and B,
No, not to all of them, but you can jump. You can have jumps like that. You can even have jumps like that. But
the jumps have to be some finite distance?
no. You can jump wherever you want as long as you're connected.
But then what's the difference between zigzag connected and light cone connected?
Light cone is just once. So, for example, if this is the light cone of A and this is the light cone of B, then A and B are not light cone connected, but they may be zigzag connected through C.
And they're zigzag connected as long as there's at least one such C?
If there needs to be a chain such that there needs to be a chain.
Does that mean that there has to be C's every whatever, some number?
No. Just a chain of qubits, A1, A2, blah, 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 up to B, such that AI is light cone connected to AI plus 1.
Yeah, but the number of sites in between have to scale with
It doesn't really, no scale, just nothing. I don't require anything, just, it could be, so first of all, it's not a priori clear that it's monotone, meaning that you don't have to jump backwards. It is monotone, actually. But even so, I mean, if those are very, very far apart, you can have a very large jump, or you can have many, many small jumps.
So you say I can't have only one extra jump. So how many jumps? How do I know how many?
Unboundedly many. I don't know. This is hard. I don't know.
But there's some lower bound on how many jumps to qualify as zigzag?
Maybe for the sake of time, we should move on to wrap up, and we can go to discussion after.
Yeah. So let me wrap up and by first of all a vote. What do you think? Is it close to? So is there an intermediate phase or no? How many think that there is an intermediate phase? How many think that there is no intermediate phase? Okay, so good. The answer is, in 1D, the answer is probably depends on the dimension. In 1D, there is no intermediate phase. That we know how to prove. Intermediate phase, in the sense that we showed, somebody asked you, I think you asked it, we don't actually know that this corresponds to the phase, the physical phase, because we don't have a physics explanation of what it means to have a classical simulation. So we don't really know that below the zigzag point there is no classical simulation. We don't really know that below this light cone connectivity there is no quantum memory, even though it's tightly related to quantum memory, because this is basically connection to your past. But we don't know that. But there, in 1D there is a phase transition, a single phase transition in those definitions, meaning the zigzag connectivity is the same as the light cone connectivity. I'll show you in 1 second why that is true, and the reason I want to show it to you is because that's convincing for why it probably depends on the dimensionality, and probably in 2D there is an intermediate phase. So how does it work? Very, very simple. The argument basically says that you want to show that if we are above the light cone connectivity threshold, then the probability for a large zigzag connectivity is small, exponentially small in the distance. How does it work? So if we're above the light cone connectivity threshold, and you want to connect these two guys, A and B, with zigzag connectivity, well, you can divide it into two cases. One is that there are big jumps. The other is that there are small jumps. Big jumps are ruled out by the fact that we are above the light cone connectivity threshold. Small jumps are ruled out by the fact that if they're small, then there must be many of them. And if there are many of them, Well, you need to make it independent, so you need to take only once every 2 jumps. But there are many second jumps. They're independent. And the probability for such second jumps, if they're independent, is raised by the power of their number. And all I have to show is that the probability for 1 jump is less than 1, and then it will decay exponentially. Okay? So that's how the argument works. Okay, so to wrap up, we know in 1D that there is no intermediate phase as I define it. I conjecture that there is an intermediate phase in 2D and above. It seems to be compelling, but I admit it's not a proof that there is one, even if we show it in the statistical model. But there is something very physical, I think, in the light cone connectivity threshold argument, and maybe also in the zigzag connectivity that is less convincing. And I think a very, very important open question is actually to find a more physical description of those thresholds. Thanks.
For the sake of time, just one question, I guess.
So if you change the definition of entanglement, is this going to change? Is this sensitive of your specific notion of entanglement? I guess here entanglement of formation.
No, I mean most entanglement notions are going to be happy with this definition as long as you have a mixture over. I mean, this shows that you're epsilon close to something which is tensor product. So as long as it's continuous.
Okay, if you want to talk to her more, you can do it after. And I guess people want to go for lunch, so let's wrap it up. Thanks again.